Hey everybody, I'd love to introduce Matt Kotchen from Yale University, who's been connecting the economics of decarbonizing the world to the reality of actually the physical actions we have to take. Welcome, Matt.
Great. Hi, everybody. It's a pleasure to share my work, and Greg, thanks for the invitation. I am a environmental and energy economist here at Yale. I've been in government, worked at NGOs, and lately I've been doing some work on electricity markets and climate change topics, and I'm happy to present some of this work. I assume that this is sort of an interdisciplinary group a little bit and not just straight up economists. So yes. I'll try to focus on some of the just kind of like broad themes and give you some of the results. And there's sort of some computational aspects of this that are, while challenging to us, maybe are not challenging to you all, but maybe something that could seed potential ideas for types of things that the types of programs and different types of things you work on. So I think that's sort of interesting. And please ask questions or interrupt anytime throughout. So I'll shift to share mode here. Hold on, now I seem to have lost the option. Here's screen one, allow. So are you all seeing my screen now?
Yes.
Okay, great. All right, I can't see you the way this is working out. I don't think so.
I'll just pipe up.
Yeah, just pipe up if something comes up. Okay, sure. So this is a project on the feasibility, costs, and benefits of an immediate phase out of coal for U.S. electricity generation. It's joint work with Stephen Holland and Andrew Yates, who are both at the University of North Carolina, and Aaron Manser, who's at the business school at Dartmouth College. And you'll see that this is a little bit of an unusual project for, at least for economists like us to work on, because in a sense, we're really kind of, instead of solving for what is the bread and butter for economists usually of trying to figure out what is optimal policy, we're actually kind of just focused on feasibility of a particular policy that one might be interested in the very short term in order to rapidly reduce greenhouse gas emissions in the US from the electricity sector. So by way of motivation initially, so the paper is focused on coal, and you'll see also natural gas and the interplay between the two. But this is a graph that just shows back from like all the way 1750 all the way to near present time, showing us the types of the sources of global greenhouse gas or in particular CO2 emissions. And you can see on the bottom here that coal still comprises the lion's share of CO2 emissions globally. So there's a lot of talk about how coal has been reducing, and it has been in the US, as I'll show in a moment, but it's still one of the big ones for CO2 emissions and also for the other local pollutants that are less of a concern for climate change, but more of a concern for human health. Here is a slide that is showing the future of coal for electricity generation. And if you look at the International Panel for Climate Change, the IPCC, and also the United Nations, it's basically considered vital for most that reducing the amount of coal that we use for generating electricity is considered a priority objective, and in fact necessary in order to meet many of our greenhouse gas reduction targets. And so at a recent United Nations, the COP26, there was a pledge among 45 countries to actually phase out coal for electricity generation. The US was not a signatory to that agreement of 45 countries, but it turns out that there are many states in the US that actually have implemented plans for a phase out of coal. And this is California, Maine, Oregon, Texas, Washington, New York, and Hawaii. And this map just shows you a summary of all countries that actually already now are coal-free, those that have phase outs by 2030 and phase outs by 2040. So there's increasing and growing pressures for countries to do something about the use of coal for generating electricity. What has happened in the US recently? Well, this is a graph showing you from 1950 up to 2022. And this is how we generate electricity in the US. And you can see that since, actually around like 2009 or so, it is true that coal has dropped precipitously as we've had an increase in the use of natural gas primarily, and then renewables for generating electricity, but coal still is a major source of energy for electricity generation in the US, comprising about 20%, or at least it did in 2022. And I think despite this drop that many people talk about has led to significant emission reductions, the question is, are we on a path to a natural phasing out of coal without any sort of policy interventions? Or if the US was to make a pledge and think about reducing coal, would it require some sort of policy intervention? And we sort of argue in this paper, which by the way is available on my webpage for those who want a deeper dive in some of the things I'm talking about, that coal is not at any time soon on its way out for US electricity generation. And part of it is because the increasing push for electrification, with electric vehicles being a prominent example, also the expansion of data centers, which you all probably know a lot about. In the US, we're also beginning to export our natural gas through the use of liquefied natural gas more and more. So our natural gas is not only going to be use for electricity in domestic markets, but also internationally. And despite the push for more and more renewables, there needs to be more and more use for dispatchable sources of electricity to follow fluctuations in demand and changes in weather variability. Now, with the extent of batteries continue to expand, that this actually could change. But right now, given where battery technology is right now, we think that there's going to be a continued need for dispatchable sources, which are going to be the primary sources that we have for that are both coal and natural gas generation. This actually shows the reduction. I'm going to just skip this slide in the interest of time and jump to our research questions. So what this paper is about is how feasible is it for the US to phase out coal in the short term? And by the short term, we mean using existing sources of generation that we currently have now. And this will include both, as we'll see, existing power generators, but also the existing pipeline for distributing natural gas that we have right now. Like, is it possible right now, if we wanted to turn a dial, to eliminate coal from electricity generation in the US? And if not fully, how far can we get? And then what would be the costs and what would be the benefits of doing that? And then also look at some of the distributional consequences of where locations that would benefit from this and where locations that would not. And then the last, which is more of an economist way of thinking about the question, is this is a bit of like a blunt force instrument, I would actually say. But then how would such a policy compare to a price-based instrument, which is a carbon tax, which is sort of the focus of most energy and environmental economists as the policy instrument that would be most desirable, precisely because it is often the most cost-effective approach. And I think that this paper, sort of interestingly, despite the fact that many find this like a pretty natural and interesting question, it's an understudied topic and one that hasn't received a lot of attention. And part of it is because economics and engineering models are typically not well equipped to deal with such non-marginal changes. Usually economics and engineering models are calibrated to say, well, what happens if you roll in a policy over time and do gradual adjustments? But this is a non-marginal change where we, as I showed you before, we still use coal to generate 20% of our electricity. What happens if we try to eliminate all of it right now? And because I already sort of indicated when I mentioned this third question, economists tend to focus on incentives rather than mandates. And I think there's also a concern among many that focusing on natural gas to replace coal is kind of a bit of like, you might think of, for those concerned with climate, a bit of like a deal with the devil, in the sense that it may result in short-term emission reductions, but could create a lock-in effect that would actually make it more difficult for renewables later. And to this question, I just really want to emphasize that we're focused on using existing sources of generation and pipelines. So we're not talking about building out new capacity for natural gas for power plants that would then stick around for potentially decades into the future. So that's the setup, that's the questions. Here's how it relates to where other studies have been done. I'm just going to focus on these last two bullets. I think most of the approaches that kind of come close to answering these questions are long run. These are sometimes referred to as grid dispatch models, where you actually have a very detailed and complicated models of the energy system for generation and dispatch. And these models actually turned out for reasons I just mentioned before, are not good at looking at non-marginal, non-gradual changes. So this is some of these models. We've actually talked to people who run some of these. Plexos is one, or there's the actual ISO models in the electricity sector. And some of them said that the types of question that we're interested in this study can't readily be done with these models because they're just not equipped for dealing with such a discontinuous change. There's also a literature where they focus on short-run changes in electricity dispatch. But as you'll see in a minute, I guess I would say the lens that we as researchers use in this paper is not to have these complicated grid dispatch models, but we actually used revealed preferences for observed behavior on the electricity grid to infer counterfactuals of what could happen. So it's methodologically different in a very, what you might think of as a reduced form approach for answering the research questions here. Here's just a graph to show you a little bit about what the challenge and what we're sort of doing here. So we're going to be focused on net load, which is basically the demand for electricity in a particular region, where we subtract off renewables and other hard to dispatch technologies like nuclear and hydro would also, in most cases, would be an example. So what we've got here is this is in the mid-Atlantic region in the US, and this is the generation that comes from only sources of generation, which are coal and natural gas, okay? And what this curve is we have estimates of the marginal cost of generating electricity from subbituminous coal, bituminous coal, so different forms of coal and different technologies of natural gas. So this is combined cycle gas turbines, steam gas turbines, and peaker units, which are sort of good for ramping up when electricity demand spikes to quickly ramp up the amount of electricity generation. And what we've done here is we've ordered these. This is referred to as a merit order, or sometimes a dispatch curve based on marginal costs, where we've just added the generation capacity here with increasing marginal costs. And historically, it used to be the case that coal units were the low-cost generators and natural gas units were the high-cost generators. And that's true for these peaking units, but it actually turns out that these combined cycle gas units are actually lower than many of these coal units. And so the idea here is you line this up, and if you are cost minimizing, okay, you would meet demand. And what this curve is telling us is throughout the year, and this is the year 2022, this is a distribution of the amount where electricity demand was. You can see the peak is the mode here is around, just under 50 gigawatts in the Mid-Atlantic region, but there is a tail. And all of this is generates capacity that could actually meet this demand. And one of the things that we're actually going to do in this paper is ask what happens if we do priority dispatch such that the natural gas units, regardless of their cost, always get priority dispatch over coal in order to meet this demand. And we're going to consider, is there enough natural gas capacity to meet the coal generation, or is there not? And if we use it, what are the costs associated with using it? So that's kind of like a bit of the setup. Yeah, go ahead, Greg.
Yeah, just to understand the relative the complexity of using these things. So first of all, you took out all the power that was generated by solar and wind because it was just incredibly noisy, I'm assuming, and nuclear because you just never turn it off, and you focused on everything in between. Is that fair?
Yes, but it's one of the important things to realize is that we've netted it out both in the supply curve here, but also the demand curve.
Right, like take away all the demand that's satisfied by that supply
Exactly.
that you don't care about today.
Exactly. So we're talking about this. You could think of this as like, what is the electricity demand? Sorry. Here, what's the distribution net of everything other than coal and natural gas?
Cool.
And that's this. And this is just the suppliers that come from coal and natural gas. So it's almost as if we're separating the two markets.
Good. And it makes sense. Then in terms of the switchability of these technologies, I know gas you can turn on and off pretty much freely, but it seems like coal, it depends on the technology, how flexible it is.
Yeah. So one of the things that's interesting, and this sort of comes from some of our complementary work to this, is it used to be that coal plants are actually used because it's difficult to ramp them up and down
Right.
to meet base load, and you would use the peaker natural gas units to meet demand. And that's still true with some of the peak units, but increasingly, because natural gas plants and natural gas prices are such, I mean, they're not now as much, but they have been over the recent years, that increasingly coal is being used to ramp up and down to meet peak load, and gas is actually being used to meet base loads. That's one of the things that has shifted over time, where gas generators are trying to do whatever they can in order to actually kind of like stay in business, and doing that ramping, although inefficient, is still the way for them to actually, still stay in the action.
That makes sense. And then last one is because this frequency is going to be minute by minute, hour by hour. What temporal resolution are you using?
We're going to do this analysis hour by hour, and then we're going to go through some tests sort of at the end to show that doing the type of analysis that we're doing hour by hour doesn't seem to be all that binding in terms of violating ramping constraints at natural gas and coal generators.
Interesting. Okay, thank you.
Sure. All right, so here's just a bit of economic theory about what is going on here. So this horizontal axis is net load. So this is basically the demand for generation from coal and natural gas. And we've got a vertical axis. This is our just sort of like money metric. And if you actually think about what is an observed equilibrium between how you split between your coal and natural gas generation, this curve here, this MCC, this suggests the marginal costs from coal units, where it's ordered such that it's increasing marginal costs. That goes from left to right. From right to left, what I've ordered is the marginal costs from natural gas units. And in order, the equilibrium, the private equilibrium that you get from natural gas and coal units would be the intersection between these two, assuming cost minimization or a perfectly competitive market, where the intersection of these curves would suggest that of this net load, this is how much you meet with coal, and this is how much you meet with natural gas. Okay. Now, one of the things that we're going to do is we're going to say what actually would happen if we said natural gas always gets priority over coal units. Okay. Now, it turns out that we've drawn this marginal cost curve for natural gas such that there is enough capacity to meet all the net load from natural gas. So if you actually did this priority dispatch and you generated all from natural gas, you'd end up at an outcome where it would just be here, 0 coal and all natural gas. And then we could ask, well, what is the welfare? What is the benefit of society? Well, now what we'd be interested in is not just the private marginal cost, but the social marginal cost, which accounts for the external, the climate damages and the public health damages associated with pollution. So the marginal cost curve shifts up for natural gas, but it also shifts up for coal. But it shifts up for coal more than natural gas because coal has higher emission rates of both CO2 emissions and also local pollutants. And if we move from this point all the way to this point, this would be the net gain, where we're rolling in natural gas units that have a lower social marginal cost than the coal that they're displacing. But eventually, if we forced this natural gas, we'd actually end up with some high cost natural gas units that are inefficient to replace, and we're squeezing out coal that even from a social perspective, we might have wanted. So the welfare gain is going to be the plus this green minus the red. And this is a case where we actually have successfully reduced all of our coal generation because we had enough spare natural gas generation. Just two other variants of this graph. What happens if there's not enough natural gas generation spare capacity around? Well, then you might not get into the red zone. You just have this green zone. You could also ask, well, what happens if the cost of that natural gas was really high, say because you actually had high natural gas prices? Well, if you do that in this case, your green area is actually going to be relatively small compared to your red area. And in this case, this is a case where you can't replace all your coal generation. And in fact, replacing it all the way with as much gas as you can might actually have a net welfare cost because natural gas is very expensive. So one of the things we're going to do in this paper is look at these different outcomes and basically estimate these different areas. Okay, some just rough descriptive statistics to try to pique the curiosity about whether or not, in fact, this is possible. So the US electricity grid is structured into different sort of transmission areas, these NERC regions, where electricity is traded within these different regions quite readily with like distribution costs and line losses, but these are common trading areas. So if this is for 2022, the year when we started this project that we had the most complete set of data, and this is the Mid-Atlantic region, which is actually the same curve data that I showed before. On the average hourly generation that comes from coal in the Mid-Atlantic region over the whole calendar year 2022 is this. And interestingly, this is how much spare natural gas capacity there is over all those hours. So it's like suggestive. There's a lot of reasons why this graph is misleading, but it looks like there's a lot of natural gas capacity compared to the coal generation, maybe about twice as much. Same with the Mid-Atlantic and the Northeast. There's very little coal generation, a lot of spare gas capacity. In the Southeast, looks like there's about 3 times as much spare natural gas capacity as there is coal generation. In Texas, in the West. So this is averaged hourly over the year. This graph takes every hour of the year over 22 and actually plots when there's a surplus and when there's a shortfall. So the green areas are in where there actually is sufficient natural gas capacity, and you can see it's above the zero line, and the red is when we dip below. So you can see in the Northeast, every hour of the year, there's always enough spare natural gas capacity. In the Southeast, it's close, but for some hours in the summer months. And in the Mid-Atlantic, Texas, and the Midwest, a little bit in the winter, but basically most of the time when you really have not enough natural gas capacity to cover your coal generation is in the summer months. And this is when you have the highest peak demand for electricity from, say, air conditioning is probably a big feature that's explaining this, although there is some of it in the winter as well. Okay. Now, one of the things, there's a couple different, we're doing different scenarios in this paper. And one is like, what is the replacement region? So if I have a coal plant, say, in some areas, most likely it's actually here in the Midwest, where is the geographic area where a candidate natural gas unit could actually substitute for it? Now, we can look at the 3 main interconnections in the US. You could look at just within the NERC regions, which is what I just showed you on the graph before, of which there's 6. You could also narrow the geography even more to NERC subregions, or you could look at balancing authority, just within balancing authorities within which there's 51. So electricity does trade all the way within interconnections, but it's more likely that you're going to find a feasible substitute within a balancing authority, or as you make this geography smaller, because there's less uncertainty or potential congestion along the transmission networks. We're going to consider how our analysis is sensitive to different assumptions about these transmission regions.
So a question at this point.
Yep.
Some of the DOE and like simulation, I'm also thinking like GridLab-D, they do a lot of the stuff where they account for the transmission lines and say here's a localized, what's it, the cost of power and that kind of thing. Why do it at the kind of regional granularity as opposed to a grid transmission line, like a graph granularity?
Sorry, I thought I understood the question. Can you give it to me one more time, Greg?
So I'm thinking when you have a graph-based simulations like GridLab-D and all those DOE models that kind of try to capture the power transmission process, they account for a lot of this. Like, what would be the levelized cost of power from all my generators, which now have more gas, less coal, in this location where power is demanded. They can account for the limitations of transmission lines.
Yeah. Okay.
So Courser here, which is a regional-based model. So what's the choice? What's the reason for this choice?
Well, this choice, so we're sort of like trying to cover like the space of different policies. Now, I think you're one way that I interpret your question is if this is basically like a research question in a project about how would you use, grid dispatch models, try to account for all of these different transmission constraints. Mm-hmm. Why not actually use that tool to answer that question? Okay. And my first answer to that is because we tried. We're not experts at using those models, but we talked to the people that do run them, and they say that they actually they think that the question that we're asking would crash the models. It's too far away from the equilibrium that they have.
Okay.
Okay. Now, whether or not that's true or not, I think, that's a research program. And one of the things that we're hoping to contribute is maybe like our project can actually spur them to start study this and use those models to answer this question. But we're sort of answering the question in a way that the best that we can, which is not using those models. So that explains why we're considering these different regions.
No, that makes a lot of sense. Thank you.
Okay, sure. All right. So here's the bit of the approach. So this is the organization of the approach. There's a lot on this graph, but I'll kind of take you through it because it sort of suggests that we're not just looking at varying geographies, but we have kind of like what we refer to as like a revealed preference approach for defining what are the candidate natural gas units within a geographic region that could possibly substitute for a coal generator. So I've got a very simple setup where this is like capacity. So this is like that merit order curve that I described before, where the green lines here represent natural gas generators and the black represent coal. So this is a region. You can think of this as like a NERC region, for example, where there's just 1, 2, 3, there's just 7 generators that are there. And I've got these circles here to represent this is like what we observed for a given hour. Let's assume in this hour that we observe this coal generator turning on, this coal generator turning on, and this natural gas generator turning on. Okay, and they all have the same capacity. That's why, to keep it simple in this just initial example, that's why their horizontal distances are all the same. One thing that you observe is that despite the fact that we have an increasing marginal cost curve like this, they're out of merit order. And in fact, there's a lot of out of merit order generating that you see, which is why we actually are going through these things. This could be because of transmission constraints. This could be because of dynamic considerations. It could be because of forced outages for like operations and maintenance. But let's just say that this is the observed generation that we get for that particular hour. And we're going to have 4 different solution approaches that we're going to show. One is a typical way that this is modeled in a lot of grid dispatch models is just to assume that you have efficient grid dispatch. So what we've got is the policy here is priority dispatch for natural gas over coal, meaning that if a natural gas generator is out there and wants to supply, it always gets priority over coal. It's not a coal ban. It's just that natural gas would always be the one that's taken over coal. The unconstrained approach is that you then have these two low-cost natural gas units replace these two coal units. They're the unconstrained because we're doing it in a cost-minimizing way. We turn on this low-cost one, and we turn on this low-cost one. This natural gas unit still stays on because the only policy that we've changed is priority dispatch for gas over coal. I want to just point out one undesirable feature of this solution concept is that now we have this as our observed equilibrium, which is observed because there are real constraints out there in transmission. But then if we modeled this as the solution, we'd replace the coal units with natural gas units, but we'd actually do it at a lower cost than what we observed. That suggests that we're missing something because we're actually like adding a constraint, but lowering our costs, which is not a desirable outcome, at least from a revealed preference economics way of thinking about the problem. So our second solution concept is going to be a revealed preference own price. And what this one says is you can only use a natural gas generator to replace a coal generator if its costs are higher than the coal units. So in this case, this gas unit stays on, but now we use this gas unit here to replace this coal unit and this one to replace this coal unit. And we've replaced both, but the costs are now going to be higher than they would with unconstrained by definition because the costs had to be higher. You had to have a higher cost gas unit replace coal. You could use the same logic and say within this region, any gas unit that turns on has got to be higher than the maximum coal generator. So now this one no longer this one no longer qualifies. If you want to replace both coal units, you've got to turn this one on and this one on. So then we've got these three are the modeled equilibrium with the revealed preference max coal. But you could even go really stringent and say any unit that turns on has got to have a higher cost than anything that we observe, in which case we'd only turn on this unit and we still keep on this low cost coal unit because there actually just isn't more capacity around to replace coal unit. This is one of the approaches that we consider as well. Any questions about this? Because now I'm going to go through and we're going to sort of look at different geographies and different replacement and different solution techniques.
Cool. And the motivation for this is that you had artifacts that your cost models were incomplete. So this is a way of correcting for that incompleteness.
We don't observe all the costs that are out there. And so this kind of like unfairly like eliminates all those unobserved costs. And these are ways of kind of like saying that that there's more and more cost constraints that we don't observe with increasing stringency from top to bottom.
Got it. And it would be things like transmission constraints, local tax incentives, things like that.
Tax incentives, but it could be like, some units have, they actually can't generate all their capacity because they need more operations and maintenance. I mean, it's the same possible of like why we actually see this gas unit generating instead of this one in the observed equilibrium. We don't know. But to move to a world where we actually assume cost minimization and no constraints, we know that that's wrong based on the observations that we actually just see based on the observed equilibrium.
Got it. Makes sense. Thank you.
Sure. All right. So here's a bit of notation of which, I'll go through this with there's a couple of like steps, but the picture is going to come through even without the formal notation here, where this is for coal units. We've got the existing generation, marginal costs, Z is their emission rate, the red is their observed generation. For gas units, we have available spare capacity. So this is subtracting off what we observe they generate. They also have their marginal cost, their emission rate, their heat rates, which is their efficiency. And then this GI sub J is a notation that says, what new generation from gas unit I do we use to replace generation from coal unit J? And we need that precisely because of the different solution approaches that we have, where it depends which gas unit is being used to replace generation from a different coal unit. And the solution is going to be this vector, which is generation from coal units and new generation from gas units. And this one's going to, the X is going to be a vector, and this is going to be a matrix because we have to keep track of which gas unit is being used to replace generation from which coal unit. And the way that we identify what is feasible for a replacement, I'm actually going to just kind of go through the words instead of the formality here, is this is basically saying you can only use the spare gas capacity that you have. You've got to generate the same amount of electricity. So any generation that we observe from a coal unit has to come from remaining generation from that coal or gas units that are used to replace it. This is saying only contender units can be used. And this is our different revealed preference solutions. And then we're also going to roll in gas pipeline constraints, which I'll talk about a little later if we have time. So one of the things we do is the solution approach that we have here is two-stepped. First is that we actually choose this vector and this matrix, the vector of coal generators and gas replacement, subject to our feasibility constraint that minimizes coal generation. So recall the priority here is to replace coal. So we're minimizing as much coal as is feasible. And then secondarily, we actually are going to be minimizing costs. So this is the key thing. It's about the feasibility of replacing coal, but we want to do it at the minimized costs. We're going to focus all these scenarios that we're going to consider. These are the replacement transmission areas. This was the interconnection NERC subregion of BA. So that you can think of this left to right as more restrictive. Then we have our unconstrained revealed preference own, revealed preference max coal, revealed preference any. I'm going to focus on these two. In the paper, we talk a lot about why we think these are the scenarios to focus on. I'm going to show you results for all of them, but we think that transmission within the NERC and NERC subregion and using the revealed preference own are the preferred scenarios. We're also going to do the pipeline constraints. This talks about our solution algorithm for how we go about just solving the problem. The outcomes of interest, we're going to look at the remaining coal generation by hour and then summarize it for the year. We're going to look at the change in generation costs, change in emissions, change in the damages, which is the value of emissions. So we're actually going to use a model that looks at local pollutants of sulfur dioxide and nitrous oxide and CO2 to actually put a value on these change in emissions. And then we're going to look at the overall net benefits, which are the environmental benefits minus the increase in generation costs. Just a word about our source of data, and then I'll cover the results. We've got hourly generation from the EPA, also emission rates. We estimate the spare capacity based on the SEMS data, which we use not based on like nameplate capacity, but we use the previous decade of observed generation to figure out how hard a plant could run. We estimate marginal costs from various data sources, and then we use this AP3 model to value local pollution, which is a source receptor matrix, which says pollution comes out of specific power plant smokestacks in a county, and then there's an air dispersion model that spreads it to other counties, and then we use the epidemiology literature is actually used to value that pollution in terms of health benefits. This is just the differences in the marginal cost between, this is different coal generators. These are the different gas generators. You can see the CO2 emission rates are very different. It's higher for coal than for gas. The sulfur dioxide for coal plants is much higher than for gas, a little bit less so based on the NOx emission rates. So this is just sort of like descriptive statistics for all the power plants for overall hours of the year in the data set. So if we run this model, we do this replacement, and this graph is showing you, assuming NERC level NERC region replacement and using our revealed preference transmission costs, this showing you at this level of geography where coal is actually being reduced. So we find using this approach in this scenario that we actually reduce 93% of the coal generation in the US in these darker areas, which is not surprisingly where the coal generators actually are, is where it's coming from. So one of the things that's interesting is even with this revealed preference approach, you can basically replace 93% of your coal generation. So this is assuming that it is higher costs. Now I'm just going to go through a couple of graphs that summarize these results. So just how to read these. This is the unconstrained, unrealistic cost minimization approach. This is the revealed preference based on the highest coal generation, revealed preference based on any, and then each of these different diamond, circle, square, these are our different geographies. I'm going to focus in on these two because I think these are the ones that are most informative, although you can see we cover quite a bit of range. What this says is regardless of your sort of geography, if you use the revealed preference approach, you can replace over 80% of your coal generation with spare natural gas generation. If you go to revealed preference coal, it's down to about 60. Even here, it's sort of like high, although it drops quite a bit. What this suggests is that our solution algorithm is actually more important than the transmission region that we actually consider. This is the reduction in coal generation. We can look at the percent reduction in CO2 emissions from the electricity sector. Using the preferred scenario, we get a 29% in electricity emissions in the in CO2 using this approach, down to like, you know, maybe 18 or 19% if we go to this region. Just remember, electricity accounts for about 25% of total CO2 emissions in the US. So this is actually quite a substantial reduction in US CO2 emissions overall. This is, so all the different scenarios result in a different quantity of emissions reductions. But we can start thinking about this from an economics perspective and say, well, what's the cost per ton? And the cost per ton ranges in this preferred. I'm going to just focus on the preferred scenario to get through the different results rather than talking about all of them where I've got the numbers called out here. Our preferred scenario is that this is going to cost you $49 per ton to reduce CO2. If you compare this to estimates of the social cost of carbon, which is what the US EPA does and the US government for official cost benefit analysis of CO2 emission reductions, it used to be $51 per ton. The revised number is $190 per ton. This suggests that at $50 per ton is the cost, but the benefits are $190 per ton. From a cost benefit perspective, it suggests that this is actually like a net winner in terms of the cost per ton of reducing CO2, at least for this scenario and even for these other scenarios.
So question, in terms of actualizing this also this is how, if this were a carbon offset, you literally paid coal to not operate, you would be on national average for about $49, although presumably different coal plants, you pay different amounts depending on the locality.
Let me just think first. So this, I think in this case, it would be a slightly different question. Say if you paid the coal plants to do it, because they may have different sort of like long-term, not hourly by hour incentives of like maintaining their like future generation over the next decade. What this is saying is that if you implemented this priority dispatch, it would cost you $49 per ton. So I understand your question. I just think it doesn't necessarily map to like, is this the cost that coal generators would accept to not?
No, fair. So
but it's close, and we could construct a mechanism that could implement it, but we need to think carefully about a broader set of incentives to do that.
So let me ask it differently. If I were paying utilities to schedule differently, is that the amount I pay them?
Closer. Okay. It's closer. It might be the way to do it is the way that I might think about it is actually if you paid natural gas generators in order to bid in higher amounts, how much would it take for them to squeeze out the coal?
Right. To enable it to, but this actually is a standard one. If you were to build a new power plant that's too expensive, how much you have to pay them for them to become the cheaper option?
Yep. Yes.
That's neat. And then the last one on this topic is it's probably, I mean, real carbon markets. Partly if you pay American power generators money, it's going to be possible but tricky. But if you pay African or Indian ones, that's a much easier sell because they're to a large extent not nearly as culpable as Americans are. How feasible is this kind of study there?
I don't know enough about this sort of like political economy and in institutions. I do know that this idea of having priority dispatch actually is in play. This is how the European Commission, they actually do in fact use this approach to priority dispatch for renewables that always get priority over fossil generators for electricity. We're basically here just saying do it for natural gas instead of coal.
Good. That makes a lot of sense. Thank you.
Yep. Okay. This is basically saying that you get a reduction in emissions at the coal power plants. You get an increase in emissions at the natural gas power plants. Where is the change in emissions and what's the value? And this is sort of an integrated assessment model that tells us county by county the value of the economic benefits associated with the change in the geographic dispersion of pollution. And that this is basically telling you where it's greatest. And you can see it's kind of like the biggest areas are downwind from the Midwest coal power plants, which you might have expected if you'd thought about this approach initially. This tells you if, let's say we ignore the climate benefits entirely and we just focus on the value of those local pollution benefits, this suggests that the benefit cost ratio, increasing costs of shifting to the natural gas units compared to the benefits of the local pollutants, the ratio in this case is just over 1, suggesting that even if you did this as a public health policy instead of a climate policy, at least in this scenario or some of these scenarios, you'd pass the benefit cost test, even ignoring climate benefits entirely. Not if you consider these scenarios, they still pass if you consider the climate benefits, but it shows that there's really local pollution public health benefits associated with replacing coal generation with natural gas. Okay, this is basically telling you, now we put on our economist hat and don't use this sort of blunt force instrument mechanism, but we basically say, let's solve this same revealed preference approach, but let's use a carbon tax instead of implementing priority dispatch. And this is basically just going through the way that we solve this problem. But the bottom line kind of comes through, well, actually, let me just jump to this graph here. This is the way to actually see it. We're going to do revealed preference, and we're going to use our NERC region and NERC subregion. And our solution, everything I talked about so far, is telling you how much coal generation is reduced. And it doesn't matter. This is different social cost of carbon estimates of 0, 50, 100, and 150. Our solution doesn't depend on this because we're just actually replacing coal with natural gas. So this is how much coal we're replacing if we use the NERC subregions and the NERC regions, more with the NERC than the NERC subregion. But then we say, well, what if we actually had a carbon tax associated that was the efficient carbon tax, and we had these different levels of social cost of carbon? And the bottom line here that I just want to get at the one of the insights here is, at a social cost of carbon of $100, basically, if you imposed a carbon tax, if compared to using our just priority dispatch approach, the priority dispatch approach gets you 92% of the benefits of the carbon tax. At a social cost of carbon of 150, it's 96%. And the social cost of carbon, as I showed you before, the current estimates are at 190. What's the bottom line of these numbers here? It suggests that even though priority dispatch is this sort of command and control approach, it's a pretty darn efficient policy when you compare it to the efficient policy of the carbon tax. It's pretty similar. So in a sense, one of the ideas here, a takeaway from this, is economists keep talking about carbon tax, efficient taxation. And the reason is that it reduces emissions and it does it efficiently. Well, it turns out in this case that priority dispatch is pretty darn close to having the same thing as an efficient tax. So if you're somebody who wants to focus on political feasibility, maybe actually imposing priority dispatch may be what you should advocate for if you think that's more likely to pass than a carbon tax. And so this is one of the things that we're hoping to communicate to our fellow economists, but also to share that this priority dispatch might actually be a pretty interesting and efficient policy. One of the things we do is we go through, we consider actual like pipeline capacity. We are replacing a lot of coal generation with natural gas. Do we actually now currently have enough spare capacity to actually do this? And it turns out, I'll just jump to this, it turns out that it's pretty darn close, even when we include these natural gas pipeline capacity. It doesn't, we basically have quite a bit of spare natural gas pipeline capacity in order to implement this. Those of you who follow these energy markets, it turns out that the one place where we don't have a lot of spare natural gas pipeline capacity is in the Northeast. But it turns out in the Northeast, that's also where we don't have a lot of coal generation. In fact, we have zero coal generation to replace. So the way that where we have a lot of the spare natural gas line capacity also happens to be in the places where we have a lot of coal generation. So this is not a very binding constraint. I mentioned at the beginning, we look at dynamic considerations, and the way that we do this, we're getting close, narrowing down on time here, so I just want to give you the bottom line instead of taking you through the specific steps. Although we solve this hour by hour, when we do so, we very rarely violate observed ramped up and ramp down rates that we see at both coal and natural gas units in the past. We also consider going back to 2019 and redo the analysis, because these are years where prices were quite a bit different. And it turns out if you go back to that time, it was even, and if we had this in 2019, the cost per ton is actually as low as $9 per ton. It's higher now. One of the key differences that matters is not the absolute level of coal and natural gas prices, but just the differences between the two. And in 2022, we had much bigger differences between coal and natural gas prices at $4.22 per BTU than we did in 2019. And we use this because it's a year prior to COVID, and also when there was a larger range in natural gas and coal prices. Just give you the bottom line here, basically implementing this short run priority dispatch, which is not the same as a coal ban, because it actually, we still keep the lights on and use coal if we need it. We actually find that you can reduce between 85 and 93% of coal generation, which is basically the equivalent of reducing between 6.5 and 7.6% of overall US CO2 emission reductions. And although what you get depends upon the transmission area and the solution concept that you use, in all cases, these policies seem to be quite efficient. And in fact, they're almost as cost effective as a carbon tax. And so we basically are on a sort of pitch here to think about priority dispatch for natural gas in the short run might be a policy that people ought to start considering and thinking about as part of the US strategy to meet its emission reduction goals. In addition to, of course, increasing renewable sources of generation and other types of storage as well. So that's basically that's all I've got, and I'm happy to take if there's any other follow-up questions that you all might have.
Yeah. So one that comes up is the power utility. So you did this essentially for a sample 2022, and you kind of did it in that year. It worked out. Now, usually these dispatch algorithms, or how much they keep paying these generators to keep power, keep staying on, is for like at 99% confidence we'll have enough power. So how do you account for that? We have to keep paying them to live, but maybe they're not generating. But how else do we make sure that they're not out, so that 99% of the time we still are up?
Yeah. Well, one of my co-authors, Aaron Manser, is kind of the expert at some of those like incentives. I guess I would say for this one, I mean, if you wanted to pay them to keep the capacity around, so it's on call, you could still keep doing that.
Right.
Right. And implement this procedure.
So I guess it would be, it just cost more. I mean, same emissions, but at a higher price.
That cost would still be the same, right? I mean, you're already paying them. Don't change that. I mean, so if you want to replace coal generation with natural gas, you could do it. But given uncertainties, you may still want to continue to pay some of those coal plants to stick around because of uncertainty.
Yeah.
So that's another way in which you really think about this as a very like short term, like those dispatch models are about like entry and exit and which capacity around. This is sort of like, we're just thinking about whose dial is changing, but not changing the actual capacity.
Right. That makes a lot of sense. And can this inform, I mean, based on the price you're computing, the value of installing one extra battery, one extra nuclear power plant, something like that? Nuclear would be just the total demand goes down. What's the value of that?
Well, if you started to have battery nuclear, and then you actually changed what we're defining as net load, which is dispatch, you're kind of shrinking the whole domain over which this whole thing would apply.
Right. So it might be an interesting forecast of the potential benefit of this under these. I guess that's how you should think about it. Under these future scenarios, their cost is whatever. Now the benefit is here. Is it worth it? That kind of thing.
Yep. Yes.
Okay. Interesting. And then, so applying this to like Africa, India, Brazil, where you have less data on all this dispatch stuff. I guess how little can you get away with? Do you think?
Oh, interesting. Maybe you were getting at this also. Another, in the US here, we have like very good grid dispatch models that maybe they can be repurposed and used to answer this question. In order to implement our approach and to think about it, you don't actually need to have the models at all. All you need to have is like data on each generator, what its capacity is, and an estimate of its marginal cost. And then you can actually do this in a very disaggregated way.
Yeah.
So this might be like a first pass on like, how does spare capacity that you have compare to what you're actually generating, to kind of begin to imagine what the different possibilities could be for using different sources of generation that would have lower emissions.
Got it. Well, yeah, thank you very much. This is fascinating.
Yeah, cool.
Yeah, have a great rest of your day.
All right, great. Thanks, Greg. Thanks, everybody. And I appreciate it, and good luck with your work.